Hello. Today we're going to be talking about Math 3 Unit 5, Objective 4, which is graphing rational functions. There are three parts to this lesson if you look at this objective sheet. This first piece, page 373 to 375, is a technology lab that you could do with your students. We've changed the directions so that it supports better what they're going to have to do on the worksheet and the later problems, so that it would lead into them being able to be successful on these. Then there's a book portion, and then there's a worksheet portion. And so I just want to show you those three parts. If you had a block day, you probably could do all three of them. Well, the worksheet will be entirely homework in any scenario, but in a block day you could probably accomplish all of that in one day. On a regular day, that's probably going to go over 2 days. You may, if you're jammed for time, decide not to do the technology lab and just do a quick introduction yourself and just do these two. It'll require more direct instruction to get them to be able to do these without the exploration in the lab. So I just want to show you each of those things so you'll be able to make good choices about what you want to do. Part 1, the technology lab, looks like this. It is set up in the book to be done with a TI-83, TI-84 type calculator. That's what these pictures are from, is that screen. This conversation about dot and connected, although it is interesting, it is not really essential to have that portion of the conversation unless you're working with very old calculators. Old calculators, as they plotted these points, when they got a point down here, the next point they would find is up there, and they would draw a line connecting them because they didn't know what happened in between. Newer calculators have greater memory, and so usually they'll hit that spot where the asymptote is, and they won't try to connect this branch to that branch. But in an old calculator that might happen, and I used to have my students change it to dot to avoid that situation. So if you're working with a very old class set, that might be a thing. Otherwise, I would say just ignore this portion of the page, and you can start right away at this problem, graph the parent reciprocal function. And so in this one, they're supposed to be learning what this function family looks like, just like they learned what a parabola y equals x squared looks like, and every other y equals absolute value of x looks like. They're supposed to be learning what that looks like. And so it can be done on Desmos or on a graphing calculator. Here's what it would look like on a graphing calculator. I actually have all of the curves already typed in here, but I only have top one highlighted, so when I hit graph, I'm only going to see that top equation, and there it is. If students aren't sure what's going on, you can hit trace, and I can see when x is 0, y has no value. You might ask students why that would be. Think about if you plugged in 0 for x, what would happen in this equation right here. And then they can trace along and see as x gets to be these decimals, y takes on these decimals. You can ask them to predict when x is 1 what y will be. Hopefully they'll be able to see that's 1 over 1, and it should be 1. In fact, they could actually type the number 1 in. I'm going to actually hit the number 1 right here, and that will make x be 1, and hit enter, and I'll find that y is exactly 1. And I can continue to do that. 2, enter. I can see that I'm at a half, which makes sense. 1 over 2 would be a half. 3, enter. I can see I'm at a third, and so on. And you might ask what's going to happen when x is 100, what's going to happen if x is negative, and you can see the graph over here is in the negative portion of y values, and ask them, does that make sense? These questions here said, examine both negative and positive values of x, describe what happens to the y values as x approaches 0. And as x approaches 0, as we get really, really small values of x, I'm going to use my trace and just slide back there. X is 0.2. Oh, there's x0, y doesn't exist, but when x is 0.2, y is about 5. Wonder what happens when x is 0.1. I type that in. Y is 10. Wonder what happens when x is 0.01. Y is 100. Might ask and see if they can figure out why that would be. When x is 0.0001, and so on. Y is getting pretty big the closer x gets to 0. And on the other side, in the negatives, They should find a similar thing. Negative 0.1 gives us negative 10. Negative 0.01 gives us negative 100. And so here y is getting smaller and smaller. More negative would be something they might understand. Okay, what happens to the y values as x increases? And so as x increases, notice the y is getting closer and closer to 0. And as x decreases in the negatives, y is also getting very close to 0. And students might remember the name from exponential functions, asymptote, that this is an asymptote, that the graph is getting very, very close to 0. Would it ever equal 0? Is there a number they could think of they could plug in for x to make this equal 0? And they should say no, we would hope. And so that exploration gives them the idea, anyway, that this is the shape of a reciprocal function, of a 1 over x function. From that, they're supposed to, according to the directions, change directions on the worksheet. I'm going to show you that. Here they are typed in, the alternate directions. I wrote them down again here for us. And what I would want my students to have on their paper, let me just move this up so you can see better, is I would want a graph. We know we had a 1, 1 here, and when x was 2, y was a half, and then a third, and when x was 1/10, y was 10, so really close here, and it went like this. Getting very, very close to 0, and then in the negatives it did it the opposite way. That would be my. So A was graph, B was state the asymptotes. This horizontal asymptote right here is the line, not y equals 1, not y equals, this is actually y equals 0. And that's the horizontal asymptote. And this one that goes up and down, because it never hits the line where x equals 0, this is a vertical asymptote that says x equals 0. Not x equals 2, not x equals 1, but x equals 0. And this is a vertical asymptote. I'll go ahead and write out the word asymptote. Sometimes I personally abbreviate those as VA for vertical asymptote and HA for horizontal asymptote, just to make writing a little bit shorter. Those are both very long words. And so we can see that those are our asymptotes, the lines that this graph will never cross. Y will never equal 0. X will never equal 0. The x-intercept, we just said it would never equal 0. X-intercepts you get by plugging in 0 for y. And so when you try that, if you had a student who didn't recognize it from the graph, they would get this. They could multiply both sides by x, and 0 times x is still 0, equals, cancel, 1. And that's just not true, and that's because there is none. And from the graph you can see there is no place where that graph intersects the x-axis. So the algebraic way of looking at it and the graphical way of looking at it support each other. For the y-intercept, hopefully they remember that you plug in 0 for x, and oh no, that's bad news too. You can divide by 0, and because of that there is none. There is no y-intercept, and we can see that also on the graph. And when you try to plot 0, you get no value. When you look at the graph, there's no value where it's hitting. So we know in both cases that there's no x-intercept and no y-intercept. And that means the domain, as I'm looking at x values, I can use about any value except for 0. If I think about the function, I could plug in any number I want there except for 0. So my domain would be all real numbers except 0. If you wanted to write that, you could write all real numbers x not equal to 0. You could do an interval notation where you did negative infinity to 0, union 0 to infinity. Either one of these two is fine, so I'm going to just circle one of them. Either one of those is fine, depends on what you prefer. And for range, I would say similarly that the y could be any negative but not 0, and any positive. So similar answer, all real numbers, y not equal to 0, because the range is y. And so that's what you're wanting them to notice. From that, we're going to go on to other graphs and figure out what happens when we change things. And so on this one, we're wondering, what if it's not a 1 on the top? And so just to kind of show you what happens in that, because we didn't teach these graphs in Algebra 2 before, if I go down to the second function and I'm going to graph it also, so now I'm going to have 1 over x and 7 over x. Graph. And the 7 over x seems to be further away. And if you actually will plot points, that will make sense to you. If I did a x, y, and thinking of things that are easy to plug in, when I plug in 0, I've got nothing. When I plug in 1, I would get 7. There's no other real divisors. But if I divide by 7, I would get 1. And so you'll notice before, when I plugged in 1, I got 1 on the old function. And now when I plug in 1, I get 7. And so basically that ends up keeping the graph further away from the origin. It's just kind of expanded there. And so as far as asymptotes go, well, we'll go ahead and draw it. At 1, I'm up at 2, 4, 6, 7. At 2, 4, 6, 7, I'm at 1. And it does something sort of like this, not getting as close to the origin. Same thing on the other side. 1, 2, 4, 6, 7. 2, 4, 6, 7. And it does something sort of like this. So students should still notice that the asymptotes are x equals 0 and y equals 0. X equals 0, you want to make sure they know which one's which. So x equals 5, x equals 2, x equals 0 is this one. So this is the vertical asymptote. And y equals 10, y equals 5, y equals 1, y equals 0 is this one. This one is the horizontal asymptote. Okay, so we'll help them think through that. If they try to find the x and y intercepts, they'll find the exact same thing they did this time. I'm just going to go ahead and write none, and they'll find the exact same domain and range that they had before, where x not equal to 0 and y not equal to 0. I'm not going to write all of those out or through those again. This one shifts, and so in this case, if you think of it as right here is going in with the x, and this is added on the outside, what I'd like you to notice is it's going to be really similar to when we did a parabola. Let me just grab a piece of paper and show you that. So when we did a parabola that was y equals 3x squared, and then we had y equals 3x plus 4 squared minus 2, we know that this thing at the end shifted us down 2, and this shifted us the opposite direction of what we expected. So instead of going positive 4, this shifted back negative 4. So we would expect to see a graph that is sort of like our 7 over x. It's a 3 over x, but it's going to be shifted back 4 and down 2. I'm going to show you that first on the graphing calculator. Let me turn off the 7. And I was trying to turn off the 7. Let me turn off the 7 and turn on this one. And that's the original. And here we have the alternate graph. It slid back 4 and down 2. And that's okay. You've gotten the kids to notice that. I really like doing it on Desmos, and I'll show you why. Although tracing around would help. My computer went to sleep, so give me a second to wake it back up. Okay. So on this Desmos screen, when I type, I'm going to type right over here. And when I type, I'm going to go y equals 3 divided by parentheses x. Look at how the 3 over x, oops, I just got 9x, let me back that up. Parentheses x. Notice how the 3 over x is there right now. And now I'm going to add in plus 4. And as I did +4, the graph automatically shifted backwards to -4 as a vertical asymptote. I really like that. Then I'm going to use my sideways arrows to get out off of the bottom of the fraction, and then I'm going to type -2. And now we see that the graph slid down too, so let me just make that a little bit bigger. So you can see I have -4 as an asymptote, and x equals -4 and y equals -2 as asymptotes. And so I really like the Desmos because I like to see the graph shift as I type. I find that dynamic part of it really easier to catch on to than in the TI where I have to type the whole thing in. But if you don't have a lot of students with phones, this is a fine thing to do on a phone. It works really well on the phone. But if you don't have a lot of students with phones that can do that, and you can't get to computers easily, then the TIs are a good way to go. Or you demoing it on your screen, that's another good way to go. So what they should find is that this is going to shift us back 4 and down 2. So instead of having a vertical asymptote at 0, I'm going to have a vertical asymptote at -4. I'm going to have a asymptote at -2. And then the graph is going to be in here and down here, not quite as tight to the pretend origin, the origin that we've just shifted, as it would be if it was